Hello students. So today we will see the part 3 of the theory of some basic concepts of chemistry. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the images and content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. If I talk about the first objective of today's class, then it would be focusing on the laws of chemical combinations. So these laws were very primitive, but if we take them as the starting point, then they were able to explain most of the phenomena and their significance was phenomenal. Now, moving on to the first topic, which is laws of conservation of mass. Then we will see the laws of definite proportions, laws of multiple proportions, and Gay-Lussac's law of gaseous volume. Lastly, Avogadro's law. So these are the laws of chemical combinations which we will talk about. Many of this are just transformations of one another. Okay, so they have been formulated from time to time so that we can get a more clear picture. Then at last we will see the first atomic theory according to the Dalton, and we will also cover its drawbacks. So first of all, we will talk about the law of conservation of mass. So this was one of the 5 basics law. This was given by Antony Lavoisier in 1789. The law says that if the physical and chemical changes are carried out, then there is no net change in the mass during the process. The experiment which Antony Lavoisier conducted to prove this law was combustion reaction. So he did the combustion reaction, calculated the mass of reactant and products, and found that both of them are having the same masses, means during a chemical reaction there is no change in the mass. Now a more short way to say this whole sentence would be that matter can neither be created nor be destroyed. So this is the famous statement of law of conservation of mass, and this law will be used in the later on chapters also. How this law is just a formulation of our previous statement. So we were saying earlier that there is no change in mass from going to reactant to product. Means if you are taking 5 grams of reactant, you will get 5 grams of product. What are these reactants and products? They are simply matter. Okay, so we can also say then your mass of the matter is not changing, or matter is not been created or neither been destroyed throughout this journey of reactant to product. I hope you got the point of this law. And finally, this sentence was named under laws of conservation of mass. If you move to further classes or you pursue science further, you will see that this law is invalid at some point for some reactions. And the reason is that some of the mass was converted into energy. You know the relation between energy and mass. It's the famous relation E is equals to mc square, which says that your mass can be converted to energy. So the modified law would be like this, that energy and matter both are conserved. Now there is a possibility that your mass can be converted to energy. So some of your mass would not be available at the end of the reaction, but it doesn't mean that it has been destroyed. It is just transformed to the energy form. Clear? Okay. Now moving on to the next law. This law is known as the law of definite proportion. I have already mentioned about it in the previous classes, but we will try to elaborate it more. This law was given by French chemist Joseph Proust. It says that if you take a given compound, then it will contain the same proportion of element by weight. Okay, so if you take any compound, suppose you are taking water, the water has two hydrogen atom, not molecule, hydrogen atom, and one oxygen atom. These two hydrogen atom will weigh total to 2 grams. Okay, if you are taking 1 mole of molecule in that case, and the oxygen mass will be 16. Now, 2 hydrogens will contribute total to 2 and 1 oxygen will contribute 16. That will give you 80. Now, this ratio, if you take the ratio of hydrogen is to oxygen mass, it will be 2 is to 16 or 1 is to 8. Now, this ratio will be maintained in every water molecule. It is not dependent upon the source from which the water is coming out. It can be the water of river, it can be the water of your sea, or can be the water of your tap. All of this water will have water molecule in which the ratio of hydrogen is to oxygen will be 1 is to 8. Clear? Now, water was not studied by Proust. Rather, he took cupric carbonate to study his laws of definite proportion. He took 2 samples of this cupric carbonate. One of the sample was prepared naturally. Okay, it was extracted naturally, whereas the other was prepared in the lab. So it is a synthetic source of this cupric carbonate. Further, when he carried out experiments, he found that the composition of elements that were present in copper or carbonate or cupric carbonate were same in both of the sample. So it was not depending upon the source from which calcium carbonate was cupric carbonate was obtained. Now let us see that composition. So this is a table. Here is your natural sample and here is your synthetic sample. The percentage of copper in the total weight was 51.35 for the natural sample and 51.35 for the synthetic sample. So you can see that both of the percentage are clearly equal. Same for the percentage of carbon in natural sample and synthetic sample was 9.74, whereas the percentage of oxygen was 38.91 in natural one and 38.91 in the synthetic one. So this result clearly suggested that for every molecule that you take for the cupric carbonate or any other molecule, the proportion of the elements are fixed by weight. Okay. Now, next, he concluded that irrespective of the source of which we are taking that compound, a given compound will always contain the same elements combined together. So this was the second, you can say, conclusion. The previous conclusion was related to qualitative sampling, and this is related quantitative sampling, and this is related to qualitative sampling, where we are specifying the elements, that your elements will be same and their proportion will also be same. So they contain same elements combined together in the same proportion by mass. So here are some more examples of definite proportion. So in case of NO, the ratio is 1:1. Okay. So this is the ratio of number of atoms. Okay. So if we are telling that your mass is same, that means your atoms are also same. So if you are taking NO, then their weight ratio will be 14:16. If you want, you can simplify it further. It will give you 7:8. Whereas the atomic ratio will be 1:1, 1 nitrogen, 1 oxygen. Similarly, for NO2, it will be 14:38, 1:2. Now, how are we getting this 32 and 14 from the formula? We will see it later on. Coming on to the N2O, it is 28:16. For N2O2, it is 28:32. And for N2O5, it is 28:80. Even if you are aware about the atomic weight of nitrogen and oxygen, you can get it from the starting compound. It is 14:16. Okay, since it is not reduced to the simpler ratio, it is taken in the most complex form. So 14:16. Okay, that means 14 is the atomic weight of nitrogen and 16 is the atomic weight of oxygen. In case of NO2, the nitrogen count is same, but the oxygen count is increased by 1. So we are multiplying 16 by 2 to get it as 32. For the third one, we have 3 atoms where 2 are nitrogen. So 14 into 2, 28, where oxygen is remained to 16. Similarly, N2O2, both are multiplied by a factor of 2, 28 is to 32. And N2O5, one is multiplied by a factor of 2, that is 14 into 2, and other one is multiplied by a factor of 5, giving us 80. Okay. Moving on further. So the validity of this law was further confirmed by various experiments. Okay, so this is known as law of definite composition also in some cases, since the composition is same or the proportion, both terms can be used in the place of one another. Our next law is known as the law of multiple proportions. Now, this law is somewhat complex to understand because its statement is a bit not clear. Okay, but if you look at its example, the things become more visible. This was given by Dalton in 1803. According to this law, if two elements can combine to form one compound, okay, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. So what are we saying? That we are taking two elements and we are combining both of this and getting two different type of compounds. Okay. And if you take the ratio of any element in these two compounds, then it will be a simpler ratio. Let us try to understand this in the terms of a example. For example, if we combine hydrogen with oxygen, it can form water whose formula is H2O and hydrogen peroxide whose formula is H2O2. Now we have the same elements but they are giving two different compounds. If you take the mass of hydrogen and the mass of oxygen in case of water, it will be 2 gram and 16 gram for 1 mole of water. We will define what is mole and all. For the time being, you can think it as that we are taking 6.022 into 10 to the power 23 molecules of water. And in that amount, we have 2 gram of oxygen and 2 grams of hydrogen and 16 grams of oxygen, and the overall mass is 18 gram. Similarly, if we combine them to form the other corresponding compound, which is hydrogen peroxide, then in that case, the mass of oxygen would be 32 gram, whereas the mass of hydrogen is still 2 gram because their formula has a difference in the number of oxygen and not in the number of hydrogen. The number of hydrogen is 2, but the number of oxygen is 1 in case of water and 2 in case of hydrogen peroxide. That is the reason the mass is getting multiplied by a factor of 2. Now just try to take the ratio of hydrogen in both these compounds. It is 1:1, whereas in the case of oxygen it is 1:2. So these ratio are simpler ratio, and the ratio that we are talking about in the law of multiple proportion is the same. And this is our overall law, that if you are taking the ratio, then it will be a simpler ratio, not a complex one, if two elements are combining to form two different compounds. I hope my point is clear about this law. So the same thing is mentioned here also, that the ratio of hydrogen is 1:1, or you can also say that it is fixed, whereas the oxygen's ratio is 1:2. Then our next law is Lusak's law of gaseous volumes, and it was given by Gay-Lussac in 1808. What did he observe? He observed that if gases are combining in a chemical reaction and they are combining to form a different compound, then in the process their volume are present in a simple ratio. But the gases should be at same temperature and same pressure. What is the meaning of this? This is saying that if you are taking two gases to combine to make it a different compound, then the ratio of these two gases will be a simpler ratio. Simpler ratio means 1:2 or 1:3, like that, not in a complex manner like 1:2.33. Okay, so it will always form a simpler ratio. Suppose, for example, if you want to form water, then you have to take 100 ml of hydrogen and 50 ml of oxygen to give 100 ml of water vapor. Water vapor or water, both are same in the sense of their constituent molecule, only the state is different and the intermolecular interactions are different. So these are the two gases that we are taking, hydrogen and oxygen, and their mass volumes are 100 milliliter and 50 milliliter, whereas the volume of the water vapor that is being formed is 100 ml. So this would be the reaction equation for our given condition. Now the volume is present in a simple ratio for the case of hydrogen and oxygen, and it is 2:1. You can simply divide 100 by 50 to get this ratio. So this was the point that was being given by Lusak's law of gaseous volume, that the volume of the gases which are combining to give a third compound are present in a simple ratio, like in this case it is 2:1. Our next law is Avogadro's law. Now this law is very, very important for your upcoming physical classes. It says that if you are taking two different gases, okay, it is not dependent upon nature at all, and if you are taking equal volumes of these two different gases and at the same temperature and pressure, then both of them will contain equal number of molecules. We will try to explain it with the help of an experiment. But here, Avogadro made a distinction between atoms and molecules, which is quite understandable in present times. So suppose if we consider the example of hydrogen and oxygen and again to produce water, we see that the volume of hydrogen combined with one volume of oxygen to give two volumes of water. What is the meaning of this? So if you are taking 50 ml of oxygen, we are taking 100 milliliters of this oxygen, hydrogen. That means for one volume of oxygen, we are taking two volumes of hydrogen, and it was giving two volumes of water. So this is a simple ratio term that has been put here or used here. Now, this is the pictorial representation of what I am trying to explain. In this case, if you see that if we are taking one volume of hydrogen and one volume of hydrogen in other case and one volume of oxygen. So these are the combinations. So if you combine one volume of hydrogen and the second volume of hydrogen, you will get two volumes of hydrogen. Now why I have written it separately? From this, the point that I am trying to make is that 1, 2, 3, 4, 5 is the count of hydrogen molecule in one volume of hydrogen. And the count is same for the oxygen molecule. And why it is same? Because the volume of these two containers are same and their conditions of temperature and pressure are also same. The same thing can be said for the hydrogen. Okay. And if you see the last one, then when we double the volume, the molecules also get doubled. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So if you count, there are 10 molecules of water. So we can say that since these two volumes are equal, they will contain the same number of molecules independent of the nature of the molecule, given that temperature and pressure are same in both the containers. Now, Dalton and others believed at this point that atoms of the same kind cannot combine. So this was a myth that atoms of the same kind cannot combine, and molecules of oxygen and hydrogen containing two atoms do not exist. According to Dalton, two different type of atoms can only combine to give a compound, not two same type of elements. Okay, two same type of atoms can give a molecule. And Avogadro's proposal was published in the French journal De Physique. But in spite of being correct, it did not gain much support because of the existing Dalton's law. Now, what is this Dalton's law? So, if you just see Dalton's law, it is just an outcome of all the laws of chemical combination. And for this reason, Dalton's law was much more appreciated. We will see this law now. So, the famous statement of this Dalton's law of atomic theory was, matter is composed of a small indivisible particle called atomia. The same matter which we have discussed in the previous section is composed of this small indivisible, means which cannot be divided further. And this atomio word itself has this meaning of indivisibility. Now, this was the point that was given first by Dalton in 1809, 1808. Along with this, he has some postulates which has been published in the new system of chemical philosophy. So this was just philosophy, okay? The experimental proof of this law was not there. So the first postulate, again, the matter consists of indivisible atoms. This atomia word is replaced by atoms now. And all the atoms of a given element have identical property. So if you are taking an element, then every atom that are present inside that element will have the same property, including the mass. And atoms of different element differ in mass. So two different elements cannot have the same mass. Third is compounds are formed only when atoms of two different elements can combine in a fixed ratio. So this was the drawback of Dalton's. Okay, now compound at that time was considered as molecule only, means molecule term was not introduced at that time. Every combination was termed as compound, but later on the molecule concept came, and that concluded that the combination can result in compound and element both. So we have seen what are the molecules that comes under this compounds. So he described a chemical reaction in terms of reorganization of atoms. Reorganization means, suppose initially we have a different setup of this hydrogen and oxygen molecule. Now they are coming together in a different fashion to give us the molecule of water. Now these atoms are not created, neither destroyed. So they are just reorganized in a chemical reaction. And this is also a setback of this Dalton's atomic theory. The first statement itself is a setback, and this statement is also a setback today. Why? Because now in some reactions, the atoms are converted to from one form to another, and the example of that reaction would be the radioactive reaction, where we are changing the atom to a different element completely by release of alpha and beta and gamma particles. Okay, so this were the most important points of the Dalton's atomic theory. But later on, this Dalton's atomic theory has some drawbacks which were seen as a result of the experiment that were conducted after the proposal of this atomic theory. But still, since it was the first atomic theory, so you must know that how this atoms came into existence. So Dalton's theory, although it was reflecting some of the laws of chemical combination, as I said, but all of the laws were not explained by this Dalton's law of chemical combination, and this was the major setback. For example, it could not explain the law of gaseous volumes, and he was not providing any reason for the combination. He said that the atoms would reorganize, but what was the driving factor for that? It was not given at all. And one most important setback was that he said atoms are indivisible, means it is the last standing particle. You cannot gain any smaller particle other than atom. But we know it in our today world very well that first of all, atoms are divisible into electrons, protons and neutrons. And this protons, electrons and neutrons are also divisible into quarks. So this very idea of indivisibility was dropped after this. Okay. So this was all about today's class. Thank you for joining our session. I hope you enjoyed the lecture.